is it full skin?
No, sir.
Close to the key.
Is the slide is full skin?
Yes, sir.
So single phase drives, is it showing? Am I right?
Yes, sir.
Okay, good. So in last class we are discussing about the operating modes of different operating modes of drives. Okay, especially we are talking about DC drives. Okay, so for going to the different operating modes, so which type of configurations are needed? That is very important. Basically, in my in last class I discussing about some points about power electronics control, money power converter based control. Okay, so for our electric drives, why we are going for the power electronics based control? The main features is that if we go into the power electronics, so we can see there is a different modes of operation. Modes of operation means, is it linear mode operations or is it switch mode operations? Okay, another thing also be there that is called soft switching. So that's the in switch mode operations, that configuration is quite changing in that soft switching manner. Soft switching manner means what we can say. Suppose first we need to know about the linear converters. Suppose whatever converters we are using, so there are different range of operations, zone of operations. Sometimes there is a cutoff region, then active region, after that saturation region. Okay, so three common modes are there. Okay, common zone of operations are there. Similar kinds of thing also happened any of the system response. Okay, in open loop, any of the system having such type of response. Suppose you can consider that BH loop. Okay, so you are increasing the intensity of that current. So gradually first it was 0, then gradually it is linearly varying. After that saturation region will be there. So it is in open loop condition. Okay, closed loop, the closed loop quite different. So we have to think about that identifications. Okay, physical system identifications, how the system is performing with the response. Okay, with that what kind of response you are giving just for an open loop. Okay, so that response we need to understand, we need to see. Okay, so similar thing also happened in any of the solid state device. So initially it is cutoff region, after that active region, then saturation region. That active region, if we working and if you work, if your solid state device is working in the saturation region, then what problem you can face? That solid state device behaves like a just like a switch. Just like a resistive path. Okay, suppose in case of Mosfet, so you can say like that RD on. Okay, means drain to source voltage on state condition. So if that resistance may be minimal, okay, but high currents are flowing. Okay, so what kinds of losses you can see? I square R loss. So current is in the range of 1000, but so maybe not 1000, maybe 100 or multiplications of the 100. So can you imagine? So if you make them square, so how much enormous losses will be there? So that's why we are trying to avoid that working that switching device, working that power electronics converters in that active region. So what we will do, we are working it is either a saturation region or cutoff region. So converters may work like just like a switch. either on, either off. So what kinds of benefits are there? So you can say like that, P equal to V into I, you can say like that power. So any of the components are zero means power will be, means switch loss will be zero. Okay, switching loss will be, conduction loss will be zero. Okay, so any of them means you can say like that, when saturation region, okay, saturation region means you can say like that, it is not like exactly switch on conditions means current is flowing, voltage is zero. Okay, and switch off condition means voltage is maximum, current is zero. There is a path, there is no path, just like your cutoff region and saturation region conditions. Okay, so you are making the current, making the power, okay, that conduction power loss making zero. Okay, so unnecessary power losses will not be there. Another thing is there, when you are going for sub switching method, so forcefully you are making the current, the configurations in such a manner, okay, you are making the configuration in such a manner. So in sub switching technique, the current or voltage, any of them are, you are making them zero. So what about your significant power loss? So any of them, when that is called ZVS, okay, for zero voltage switching, okay, when voltage is zero, so at that time the switch will be turned on. So you can say like that, it is in current, the power loss will be zero. So why we are concerning about this part, about this idea? The main fact is that when we are implementing such converter in our drives, okay, so we have to think about the how much losses are there. So which type of switching pattern we are going to be used for this system. Okay, so here you can see for the different types of drives available, that availability of your source. Okay, so single phase drives means, you know that most of the cases in Indian culture, so that is your 25 kV overhead lines are there. Okay, so single phase AC is already there. And what is the return path? Return path is your railway track. Okay, so from the return path, your negative, you can say like that, body. Okay, the wheel of the rail or wheel of the locomotives is here from that way. So body, wheel, and the railway track. So it is a return path. Okay, so single phase is available. So availability of the source means single phase AC is available. Okay, and what is your traction motor types? They are in DC. Okay, DC motor, DC series motor normally we are using. So what we need to do, we have to convert that AC to DC. Okay, so if we are going to convert that AC to DC, so which switching device we need to use? Again, one important issue, what type of switching device you have to use here. Okay, so in market lot of switching devices are available. Okay, it is Mosfet available, BJT available. Okay, that I am not talking about signal Mosfet, I am talking about power Mosfet. Okay, I know that all of you have an idea about the difference between that power MOSFET and signal MOSFET or analog MOSFET. Okay, analog MOSFET means you are, the doping levels are different, the voltage range also different. But power MOSFET you are using for different high power applications, as well as high power applications means comparatively high power applications with your analog devices. Okay. So the end of the day, what happened? So what type of things are available? Okay, what types of things are, what type of devices are available? So which one is suitable for your work? So in this case, when locomotives are running, so you can see that area. Okay, that area is quite dusty. Okay, sometimes they are very cold. Okay, so cold or hot, lot of issues may arise. So you have to pick such type of devices that can control your voltage. Okay, that can rectify your voltage. Okay, as well as they are in quite robust in nature. Okay, what do you mean by the robust? Robust means suppose you say like that, any of the conditions, okay, any of the condition, it only pick its own nature. Okay, so you can say like the system is quite robust. Okay, suppose means and considering different several power devices are there. So in this case, what you can see, the rectifications are required. Okay, so here you can say that you are having single phase AC supply. Now you have to rectify to feed that voltage. Okay, that VA voltage is coming, that armature voltage that coming across of your motor. Okay, so that rectified voltage you can use that here we can use only half-wave power half-wave configurations of that one ACR we are using. Okay, so instead of ACR anything can be used. Okay, suppose you can use that IGBT, you can use also MOSFET, BJT, okay, IGCT. So you have to think which one is quite cost efficient. Okay, cost efficient means what happened. So how much costing you are given, suppose any of the damage is there, replacement is possible. So if you are using IGBT bank, okay, if you are using IGBT bank, one IGBT may cost what kinds of requirements. So you can see there is a 25 kV through, you are making them how much voltage it is coming, 750 to average voltage is 750 to 500 volt. Okay, so you know that there is a huge power applications. 750 volt means it's huge power application, and the motor is near about one motor is near about 5 HP. Okay, that may be more than that also. Okay, so you can understand that how much power application you are using. Okay, in this power range, if you are using MOSFET, that cannot be work. Okay, means that range of MOSFET normally we are using, power MOSFET normally we are using for high frequency applications, not high power applications. So we are using that IGBT is one, maybe you can use, but the costing of the IGBT may be very high. But this an amount of power may not be handled by that IGBT. So that's why you have to switch for that IGCT. Okay, so that can be handled, but they are very costly. And what about electron solid state device you are incorporating with your locomotives? Okay, so regularly that can be damaged. Okay, that can be changed, switch may be changed sometimes. Okay, so different issues may be arise. Sometimes they are not in so much robust compared to the ACR. ACR, you can see that power diode having high power diode can carry up to 500 up to 5 to 6 kilovolt, as well as near about 500 5000 ampere also, that can be handled by that one, by the power diode. But they are not so much costly, uncontrolled one. ACR, maybe ACR you can, instead of power diode, basically they are in contact, you can control the firing pulse of the ACR to vary that output voltage. So that is only required one. So okay, means if you are not able to control that firing pulse, so you cannot regulate the motor speed. Okay, so end of the day, whatever open loop system is working, that good, no problem for it. But end of the day, you have to regulate the speed of the motor. Okay, suppose current drives are using that vector control mode for that for our locomotive service. So if you are not able to control the firing pulse, or if you are not able to control the PWM width, okay, so what is the necessary, why you are implementing them for this work? Okay, so that is one of the important features. That's why instead of diode, so we can use that ACR. Okay, so that's the motivations why we are using ACR compared to other devices. So another alternative option is the IGCT. But recently you can see a lot of drives are coming with the based on that IGBT. Maybe they are reducing the voltage level of input side, they are controlling the system, and stepping down the voltage, they are controlling the system. But that high power application, that is another issue. Okay, so a IGBT set or IGCT set they are using right now. Okay, so that's the motivation by using for that SCR. Okay, for this one. So after what happened, so here you can see that armature is there, and for field winding the same configuration, that is separately excited motor. So that's why again that you can change that that SCR bridge is there. So okay, so you can rectify that value of that alternating nature and make it in DC, and you are energize the field winding. Here you can energize it, the field winding, and motor is there. motor can be also motor armature also connected with the single phase AC with that ACR band. Okay, so what are the important features for the single phase drive? The armature circuit of DC motor is connected to the output of a single phase controller. Okay, single phase control rectifier. Why control rectifier? I hope you are able to understand. The armature voltage can be verified by varying the delay angle of the converter, that is alpha A. So you can firing pulse is there. So I think you know that how to fire that ACR. So triggering, RC triggering, okay, different UGT triggering. So that kinds of triggering methods you have already gone through in your power electronics course. Still there is some aspects are there for the triggering of that ACR is quite different compared to the MOSFET. Okay, normally what we are doing, okay, suppose if you want to trigger the ACR, so first you need to you have to use some ZVS, sorry, you have to use some zero crossing detector. Okay, zero crossing detector means ZCD. Okay, so you have to use the ZCD. So I think you know the configurations of the ZCD. Okay, so suppose there are two terminals, actually three terminals, one inverting terminal, another non-inverting terminal, and output terminal of the op-amp. So you are giving the response to that op-amp, any of the terminals. Okay, so what type of response you are giving, what type of signals you are giving, that is your sinusoidal signal. And another terminal you are making them ground. Okay, now you are using unity feedback. Okay, so what is your output? Output definitely you will get the square wave. So one is ground, you are comparing, sinusoidal is now comparing with the ground. Okay, I hope you are realizing the circuit and you are able to understand. So if you are facing any problem, please tell me. Again, I will repeat. Okay, that point. So you are comparing that, what you are comparing, that inverting terminal you are giving some response, giving some alternating response, and non-inverting terminal maybe you are making them ground. Okay, now output of that MOSFET op-amp. Okay, what output you will get? You will get the square wave type of thing. Okay, when it will be zero, okay, only you are getting that more than zero, comparing them. Okay, more than zero only you will get. So one signal you will get, that is a square wave type of signal you will get. Okay, so after that what you need to do, you have to invert that signal, or if you are using bridge configuration you can invert it, otherwise you need not to invert it. So that signal is there. Okay, so square wave type of signal is there, pulse. Now this pulse should be combining. So after that one AND gate is there. Okay, after that one AND gate is there. Okay, AND gate means you can AND gate is there. One AND gate having two terminal. One terminal you are giving that signal. Another terminal you are mixing up with high frequency. That is called high frequency signal. Okay, so in that AND gate, what happened? You know that 0 into 1 into, you know that configuration. 1 into 0, output will be 0. Multiplication type of configuration. Okay, only both are 1 means you will get 1. Any of them is 0 means output will be 0. So when you are mixing up that high frequency signal, so your AND gate is there. Okay, so by that way you are mixing the signal. So after that what happened? You will get, when that high frequency signal also 1, and that your Z after output of the ZCD, that means it's a square wave, it's a 1, only that region you will get that one. So you are getting high frequency, very high frequency varying signal. Okay, but 0 to 1 variation is there, 0 to 1, but they are very high frequency after the AND gate. Okay, then what you need to do, so there is some option that is called monoshot. Okay, so you are making them what, you are just cutting, the entire cycle is not required, you are cutting them, only few of that cycle, few of the portions of that signal you are cutting them. So that signal is fed to your ACR. Okay, so normally what happen in MOSFET IGBT, you are giving some constant voltage. Okay, to running of that to running the IGBT or the MOSFET or the BJT. Okay, but in case of SCR, it's a latching device. Okay, it's a latching device. So only one signal is sufficient to turn on that device. Okay, turn on that SCR. Okay, so that's why you are using one pulse train, but the duration of the pulse train is not big, more on. So why pulse train? Suppose first pulse is miss to trigger the SCR. So second pulse can trigger it. Okay, that's why you are using pulse trend. Okay, suppose you are that's why you are using pulse trend. Okay, but why not the entire cycle? Okay, entire cycle is not required. So unnecessary. Suppose your latching device is turned on. So if you are using pulse trend for the longer duration, so all the duration it is trying to start it on. So unnecessary power loss will be there. So that's why you have to give some high frequency mixing DC signal. Okay, high frequency mixing some DC signal which having very small smaller durations. Okay, after getting the smaller duration, it can be turned on. That's the idea. Okay, so by this way you are getting turned on. Okay, so now if your firing angle is varying, so definitely that we are using the ZCS, so that also been varying. Okay, so that monoshot is given. Okay, with durations of the firing angle, you have to give in that monoshot, means with duration you are cutting down that value. Okay, so based on your firing angle, the output voltage of your SCR also varying, and that feed to your machines. Okay, means motor is there. Okay, motor armature is there. The basic circuit arrangement for the single phase converter fed separately excited motor shown in the figure. So in for separately excited motor it is showing. At the low delay angle, the armature current may be discontinuous. So definitely, so firing angle will be less. Okay, so it will be discontinuous. More means, so changing of the firing angle may be responsible for continuous mode operation to discontinuous mode of operation. Okay, would increase the losses in the motor. Smoothing inductor, that is LM, is normally connected in series with the armature circuit to reduce the ripple current to an acceptable magnitude. Okay, so smoothing inductor is there. Okay, so ripple components, so you are making them almost normalized to the constant DC value. The converter is also applied to field, also applied in the field circuit to control the field current by varying the delay angle alpha f. So for the field angle, for the field circuit also, field winding also, there is some converter, you are changing them. Okay, alpha f. So what are the configurations for single phase converter? So first one is that single phase drive may be subdivided into what are the normal configurations single phase drives. Number one is the single phase half wave converter drives. Okay, single phase semi converter drives, single phase full converter drives, single phase dual converter drives. So based on your availability, based on your requirement, you can fix it up. Okay, suppose you are designing one drive that is for that is cost efficient, very much cost efficient, okay, and not so much costly. So what you need to do, you can do that half wave rectifier or full wave half wave rectifier. Okay, then semi converter also be there. Semi converter only second quadrant operation you can go, not all the four quadrant. Okay, for only diode you can also use half bridge. Okay, half bridge configurations. Okay, so half wave configuration you can only control for the first quadrant. Okay, so if you go for semi converter, you are having options for first quadrant as well as regenerative braking options, means second quadrant, and you can do the control for the entire 180-degree cycle. Okay, for the full wave converter you can go up to full wave converter, means you can also both the cycle you can control. Okay, suppose half wave means only one part of your cycle you are working on it. For full wave both part of cycle you can convert it to the rectifier DC, and after that you can control them. Okay, but in case of dual converter, what you can do, both the operations, motoring operation as well as generating operations, braking operations, both can be possible. Okay, there is a two set of full converter. Okay, they are not back to back, they are connected to the smoothing reactor. Okay, so both the operation is possible based on your firing pulse angle. Okay, so by this way you can control it. Okay, so what is the requirement? So four quadrant operation only possible for single phase dual converter. Okay, so as per your requirement you can design your system. So here you can see half wave converter drive. Okay, so for half wave converter drives, here you can observe that one control rectifier is there, sorry, one SCR is there. Okay, so then motor drives is there. So one freewheeling diode is required for what? For that motor is an example for the RLE load. So negative voltage also be there. So sometimes that freewheeling diode is required for dissipating that negative voltage. Okay, so fuel that negative voltage. So it's your first quadrant operation. So you can see the circuit is there, then it's a voltage also positive, current also positive. So it's a first quadrant operation, and it's your armature current as there is a inductor. It's a huge values of inductor, so almost straight line armature current. Okay, so for firing angle you can vary alpha to pi maximum. Okay, maximum up to pi you can control for firing angle. The range is okay. So alpha to 5, and armature currents when it is working, okay, rest that portions armature you can say like that. Armature means it's not working, okay, when that is off, okay, off condition of this one, so there will be no armature current, rest of the portion will be there, armature current is there. Okay, so by this way you are configuring the waveforms also be there. Okay, you can get that waveform. The single phase half wave converter feeds the DC motor. Okay, so should be a diagram you can see from here. Armature current is normally discontinuous unless the very large inductor is connected to the armature circuit. That I am telling, I have already told you. Okay, freewheeling diode is always required for DC motor load, and it is a one quadrant drive. Okay, the applications of these drives are limited to 0.5 kilowatt power level. Okay, power level is less up to 1.5 kilowatt. The figure shows the waveform for a highly inductive load. As DC motor, that RLE load is there, L is very high, so it's a highly inductive load. So half wave converter in the field circuit would increase the magnetic loss of the motor with high ripple content in the field excitation current. Okay, so ripple also be there. So for the field you are using bridge circuit. So both the cycle you are utilizing them and you are charging your field current. Okay, so bridge configuration you can see. Okay, it's a semi converter bridge. Okay, so symmetrical semi converter bridge. Okay, so for ripple that one. So one cycle you can control that SCR, both the cycle you can control both the SCR. Okay, and you are getting that field wind field voltage. So here you are getting the field is there, you are energizing the field. Okay. Single phase full wave converter drives. Okay, so for single phase full wave converter means what you are doing. So instead of half bridge, sorry, half wave, you are using control full wave converter. Okay, so control full bridge or full wave converter. So you know that 4 SCR they are connected in bridge conditions, and if you giving that AC, so directly you will get some regulated. There's AC, so you will get some regulated DC. Okay, from the regulated DC, the motor is there. Okay, you can vary the motor terminal voltage and motor speed may be varied. Okay, so what kinds of thing you are observing here? The armature voltage is varied by a single phase full wave converter. Okay, single phase full wave converter. So from the figure you can see, so it's a two quadrant drive that I have already told you. Two quadrant drive means quadrant 1 and quadrant 2, first and second quadrant, both current and voltage. Okay, so current is positive. Okay, so voltage can be negative. That armature voltage can be negative in this configuration by varying the firing pulse. So firing pulse you can see it can vary up to 2 pi. So you can see pi alpha, armature current for the alpha A, it can vary beyond pi up to 2 pi, up to 2 pi it can vary. Okay, so and the application you can go up to 15 kilowatt application. The armature converter gets plus VA to minus VA and allows the operations in the first and fourth quadrant. Okay, so first and fourth quadrant it can be work up to that durations. During regenerations for revising the direction of the power flow, the back EMF of the motor can be revised, okay, by reversing the field excitations. Okay, so if you change the field excitation, so reverse direction is also possible. That's why you can see the firing pulse can be for vary from 0 to 2 pi level. Okay, both the directions you can follow. Now full wave converter. with drives. So what are another important things are there? So converter in the field circuit could be full or even dual converter. Okay, that field circuit would be the full converter or the dual converter. The reversal of the armature of the field allow the operations of the second and third quadrant. Okay, so based on that configurations of your bridge, so your converter may work second and third also. Okay, converter is highly inductive load and given in the figure. Okay, so these all are the very basic of your two quadrant operations. Okay, by using full wave converter. Okay. So field okay. Now for the dual converter, what you can see. So dual converter, you can observe there are two converters. Okay. So converter 1 is there. Another thing is that converter 2 is there. Both are connected. So in between there you can see like that their orientation is complementary each other. Okay. So suppose one converter set is connected such a manner. Reverse thing also happen in converter 2. For the field, only the full bridge is there. Field winding is energized. Okay. So what happened? You know that firing pulse. Okay, you can understand the firing pulse. Okay, so by variation of the firing pulse, so motor can be worked any of the directions. Okay, so it may be the motor voltage may be positive or maybe negative. Okay, motor current may be if positive, maybe negative. Okay, so any of the situations can be occurred. Suppose both are positive, V and I. Okay, suppose V is positive, I is negative. That is your say fourth quadrant. Okay, suppose V is negative, I also negative. That is third quadrant. Now V is negative, I is positive. That is second quadrant. Everything also possible by this configuration. So that happened only for the dual converter drives. Okay, both the alpha, both the that is converter 1, firing pulse of converter 1 plus firing pulse of converter 2, that can be work up to 2 pi range. Okay, so alpha A plus alpha B equal to 2 pi. Okay, so two single phase full wave converters are connected over here. Either converter 1 operated to supply a positive armature voltage, that VA is positive, or converter 2 operate to supply voltage with the negative armature voltage, that means minus VA, that I am talking about you. And converter 1, okay, converter 1 is there that provides the operation in the first and fourth quadrant. Okay, converter 1 is there that can be operated on first and fourth quadrant, and converter 2 that can operate on second and third quadrant. Okay, so second and third quadrant, converter 2 both are there. Okay, it is a 4 quadrant drives. Okay, 4 quadrant drives and permits the 4 modes of operation. Suppose forward motoring, forward powering, forward braking means regenerative means regeneration, reverse powering means reverse motoring. Okay, and reverse braking means again regenerations. Okay, means plugging. Okay, all the 4 conditions can be satisfied by this converter. Okay, and armature terminal A1 A2 is connected. Okay, any of the cases the field winding you can see the separately excited motor. For the series motor, what you need to do, that field winding also connected over here, so changeover switch is required for it. Okay, nothing change, only that field winding it can be connected over here for the series motor. Okay, series with your armature winding. Okay, it is limited to applications up to 15 kilowatt. Okay, so up to 15 kilowatt it is applicable. The field converter could be the full wave or a dual converter. So it can be work as a dual converter and full wave. So it's a separately excited motor. That's why field is externally connected. Okay, there is no changes for the field reversal. Only terminal voltage of the armatures are changing. So based on that, motor working has been changed. Okay, so now what is first of the cases what we are discussing about for single phase drives. Okay, so what are the limitations for the single phase drives and why we are talking about three phase drives? So very common limitations is that very common comparison is that so repeal frequency. Okay, so for the single phase drive, okay, am I audible properly?
Yes, sir. Yes, sir.
Okay, so for single phase drives, you can see when you are rectify it. Okay, so when you have rectify it, so how much for full wave or full or bridge? Okay, full bridge. So you can see how much ripple frequency it is 100 hertz. Okay, but if you are having three-phase supply, okay, now you are converting them DC. So ripple frequency is one third. Okay, so one third of your ripple frequency for the single phase drives. Okay, so that's the benefit. Okay, so ripple components. Okay, normally what we are doing, we are talking about this highly inductive load. So automatically ripple component will be mitigated by that inductive load. Okay, but end of the day, as per the configurations, the utilization is more in case of three phase compared to the single phase. Also, the problem is that the voltage, our average output voltage also very high. Okay, so that should be that you have to think about it. How much voltage means for high power application, it is helpful, as well as the ripple frequency is more compared to the single phase drive. So ripple frequency is more means that is more or less automatically automatical, that pulsating DC you are talking about, they are automatically smoothing in almost by inherent property. After that you are using smoothing reactor to making them almost fixed value, but that's the benefits for using the three phase drives, so for getting more utilizations. Okay, so same configurations also happen for the three phase drive. Half wave configurations possible, then semi converter also been possible. Okay, so full wave converter as well as dual converter, so everything is possible like your single phase configuration. So but benefit is that I am talking about, but it is the configuration is quite complicated. Okay, that's another issue. Compared to the single phase, the configuration is quite complicated. In this manner, if you compare them, okay, so connecting the smoothing reactor is you can see sometimes it is beneficial for designing some complicated drives. Okay, end of the day, some person need to be control that drives. Okay, so if some problem is occurred by their end, so it is quite difficult, okay, to handle. So the armature circuit, so what are the important points? The armature circuit is connected to the output, okay, of a three phase control rectifier. Okay, so three phase control rectifier, the three phase drives are used for high power applications that I have already discussed. Okay, so high power application, better utilization you are getting. Okay, automatically voltage level is high. Okay, high power application up to megawatt power level. Okay, the ripple frequency of the armature voltage is higher than that of the single phase drives. You can understand why it is higher than, okay, one third of your ripple frequency, that is 100 hertz, that is one third of 100, means so almost 33 hertz it is coming. Okay, it's required less inductance of the armature circuit, okay, to reduce the armature ripple current. Okay, the armature current is mostly continuous and therefore the motor performance is better compared with that of the single phase drives. Okay, so you know that motor performance automatically coming better. Okay, so basically harmonics are less. Okay, performance index are better. That is another important things. Okay, so similarly, single phase drive, three phase drive also having subdivided into four things. Okay, half wave converter. Here you can see half wave converter drives, three phase semi converter drives, three phase full converter drive, and three phase dual converter drives. These all are the very much important, interesting thing. Okay, so that portions you can also follow any of the standard books. Okay, so how it will work. Okay, so for your benefit, but I think you are able to understand the motivations of this subject and how it is working with our regular system. Okay, so that correlation is very important. So till now I am discussing about open loop system. Now we are discussing about the closed loop system. Okay, closed loop control of the DC drives. Okay, so you know that power electronics converter having two circuit. One is called power circuit, another one is called control circuit. So power circuit deals with up to megawatt range voltage level. Okay. Suppose what happened in the power circuit based on the switch configuration, sorry, based on your input voltage, given input voltage, required output voltage, what type of the inductors are required, capacitor required, solid state device required. So everything is defined. That will be in the power range. Okay, power frequency range. Okay, so they can work up to kilovolt range also. But the switch what you are using, it having some one controlling terminal. Suppose gate terminals, you can say like that, gate. So you have to provide the gate pulse. So who will provide you the gate pulse? The control circuit will provide you the gate pulse. But the power range or the voltage range of the control circuit is not more than 15 volt. Okay, it is my general idea, not 15 exactly, 18 volt, not more than 18. So what you need to do, so control circuit, whatever circuit component you are using, that all are the analog devices. Okay, and power circuit level, what type of solid state device you are using, maybe diode, maybe IGBT, maybe MOSFET, maybe BJT, they are in power range. Okay, power devices. Okay, the differences you can understand. The for strengthening the current signal, sometimes, so what happened in that gate driver, when we are designing the gate driver, so it's not like that gate driver means what we are processing that directly fed to the MOSFET or any of the solid state device, it will work. No, it's not possible. So sometimes what you need to do, we have to amplify the current level of that current. Sometimes we need to amplify the current level or voltage level. Okay, so sometimes we have to do the isolations. Okay, that I'm also coming why isolations are important. So for amplifying the current level, what we are doing, we are incorporating BJT. Okay, suppose in that power circuit also having BJT, that BJT is power BJT, and in your control circuit you are amplifying that totem pole configuration or Darlington configuration. I hope you can recall that one. So for your analog electronics, you have gone through it, I think so. Totem pole configuration, Darlington configurations for the voltage follower circuits. Lot of circuits are there. Okay, so for amplifications we are using that totem pole configuration. Okay, so in the totem pole configuration, what happened, you are if you recall the circuit, two BJT are there. Okay, so that BJT is analog BJT for using just for amplifications of your current state, and after that you can directly feed that output to your power BJT of your circuit. Okay, that is capable enough. So you know that control circuit is different, power circuit is different. So you have to sense in measurement, like that when I taught you that measurement, so that we are discussing all the time. Suppose we are taking some very common example that in biological terms of view, it is known as reflex arc. What is reflex arc? So suppose there is a hot bowels are there. So you are touching the bowel. Now your skin having some sensors. Okay, so temperature sensors or that sensors are picking the signal. Okay, from the bowel. That signal, and that signal is carrying by the sensory neuron to where, to the brain for processing unit. Okay, then you are process that value. So there is some prefixed value, threshold value is there, the temperature is there, so exact thing is not coming, whatever you have sensed by your skin, so that is some signal is there, current, some signal. Okay, electrical signals are there, so their amplitude is not so much high, it is very less amplitude. Okay, but that signals, electrical signals come to your brain, then you are processing the signal, and after that what happen, after processing you will decide, okay, what you need to do. Okay, after the processing of the signal, then if it is less than threshold value, so you are not giving any instruction to that to that actuator. Okay, so if that is more than, continuously signal is coming to your brain. Okay, so which value is, if you realize that value is more than that threshold value, then what happened? So error will be developed. Okay, error signal will be developed. So then you are trying to mitigate that error. Okay, so the controller will be there. Okay, in your brain some processing unit is there, controller is there. So if the controller is not mitigating the error, then what happened? So suddenly the huge errors are there, so it can give a response. Okay, it can send the response through another neuron, that is called motor neuron. Okay, so motor neuron to whom? To the actuator and driver. Okay, actuator and the driver. So your actuator is what? Actuator is your muscle, human muscles is your actuator. So neurons are directly connected to your hand muscle. Okay, so give a instruction, please remove the hand. Okay, So actually you are giving the signal to the actuator giving the signal to that driver. Okay, driver is there. So actuator is muscle, driver is your fingertip. So automatically you are removing your finger. So driver is your finger. Okay, automatically you are removing it. So same thing you are realize this system, closed loop system, you can easily understand. So continuously you are getting the signal that motor, DC motor is there. So speed sensors are there. Okay, so speed sensor means it's a transducer. Okay, so tacho generator is there. So equivalent that RPM you are getting the voltage signal. Okay, equivalent electrical signal. That signal is not so much high. So you have to amplify the signal to read out the signal. So that is called sensing, sorry, scaling down of your signal. Then the signal is coming, that signal sensing, speed of the signal sensing, it is written like that. So how fast it is coming. Okay, that is another important thing. And gain, that is the speed of the signal sensing means gain. So you are scaling down that value. Okay, if it is more, so you are make them less. If it is less, you are amplifying the signal. Okay, then it is coming to whom? Then you are coming to the threshold value is there, reference voltage is there. That reference voltage is given in the truth table. Okay, that given the reference RPM. Okay, here you are getting that omega is in your RPM. Okay, so here you are giving the voltage. Okay, that voltage is equivalent RPM. Suppose 1500 RPM, some voltage is given by the data sheet. In the truth table it is mentioned 1400 RPM. What is based on the set value, you are given that value. So that is called set point tracking. Okay, in control system terminology, it is called set point tracking. So you are giving the reference value. Now you are comparing them. Okay, you are comparing them and you are getting the error signal VE you are getting. Okay, error signal is there VE. So what you need to do, you know that compensators are there. In my last class, we are talking about P controller, PI controller. I'm just talking about in details discuss I am not given. I am just taking the name of that controller. Details thing you have already gone through in your control system subject, I think so. So P controller, PI, PID, then lead, lag. What is the purpose of lead controller, lead lag, where you are going to use them. Okay, a lot of controller that I am asking about classical controllers. These all are the conventional classical controller, but rest of them other controllers also are available. Suppose predictive controller, adaptive controller, intelligent controller. Okay, so different other controllers also be there. That we are talking about the robustness. Okay, so that controller robustness also dependent with the system. So temperature system. What is controller? Actually, it is RC circuit. Okay, op-amp with RC circuit. But the classical controller, we are talking about, by default, we are talking about here classical controller. For the advanced and recent modified controller, suppose sliding mode controller, they are coming inside of the non-linear controller. They are totally written in the program or totally written in the code. Okay, there are also some mathematics that you have to write here. But normally, if you physically realize the controller, the classical controller, only that is a op-amp circuit is having a op-amp RC circuit. Okay, nothing else. So in analog mode, okay, for analog platform, for the digital platform, what happened? Directly you are that signal you are giving the, so from here you are converting to the analog to digital converter and give the signal inside of your processor. Then you are giving the reference. Okay, that is quite easy to control. Then error signal will be there. Then you are using the controller. What controller you are using? That maybe you can model it or you can write a code it inside of your processor. Okay, so now controller is trying to compensate that problem. Okay, so compensate the error. Okay, if they are able to compensate the error, then you will get some control voltage. Okay, that is called VC. This first one is your VE. Now we are getting the VC, control voltage. Okay, that control voltage is now comparing with some repeating sequence. Repeating sequence means it may be square wave, or sorry, it may be triangular wave, or you can say like that it may be it may be short wave. Now we are comparing them. After comparing them, you will get some PWM value. Okay, that PWM is given that coming from that control circuit. Okay, so if it's a digital platform you are using, digital signal, digital processing you are using, so that PWM whatever generate from your inside of your computer processor, that should comes out, okay, through the digital to analog converter. Okay, now digital to analog converters are there, then isolator is there. Okay, after isolator you can feed to the actuator. Okay, so that is your actuator. Okay, and what was your driver? So then through the driver circuit for the gate. Okay, so you are giving the driver the signal passing through the driver and give the signal to the actuator. Okay, that means the gate of your or the control terminal of your switch, and based on your signal changes. Okay, so that I am also giving some examples so you can understand better manner. So it can control the output of your system. Suppose you are using voltage, motor speed. Okay, so that can be controlled. Okay, so variations if possible, so that can be controlled through the gate bus. Suppose I am taking some example. Okay, so you can understand better manner. Suppose what happened, you are suddenly increase the load, then what happened? So your voltage, your motor speed for that moment it can be reduced. Am I right? Okay, motor speed is reduced. If motor speed is reduced, then what happened? Your error signal VE, basically your reference set point tracking means you are training motor to you are trying to train motor to get the reference value of your voltage. So from that reference value of voltage giving means your reference speed you want to you want to ask from the motor. This reference speed I am it required for me from the motor. Suppose you are increasing the load, okay, then motor speed suddenly dip. Okay, then suddenly dip means what happened? So your error signal will be more. Okay, error signal will be more means compensator try to compensate. So your control signal VC also be more from the previous condition. Okay, so VC is more. Now VC is comparing to whom? The repeating sequence are there. So VC is actually what? That slowly varying. Okay, slowly varying one signal. Okay, slowly varying one signal. You can consider it's a DC value also. That error signal also the DC value. Okay, and VC is slowly varying signal. You can also consider is that signal also DC value. So that value you are comparing with repeating sequence. So suppose that DC value error signal is increasing means that VC value also increasing. So DC upliftment is there. Okay, so DC upliftment is there means what? So the width of the PWM. Okay, now the condition is that initially that DC is comparing with the triangular waveform. Okay, so now DC value is comparing with the triangular waveform, so you will get some PWM. Okay, now the DC value is increasing quite high compared to the other value from your previous value. So as per the convention, what the PWM should be more or less. As per the convention, PWM on time should be more. Okay, why? If the on time is not more, okay, so if the on time is not more, so if so motor so that converter will turn on for the less duration, so motor speed again decrease. Okay, so what you need to do, if the DC value is high means, okay, the relation will be like that, the condition will be like that, that DC value is more greater than of your triangular waveform, so you will get the higher value of PWM. Okay, you will get 1 PWM voltage level is 1, and when the DC value is less than of your triangular waveform, it should be 0, means switch should be 0. So I think you are getting the idea. Okay, so lesser value of DC means turn on condition is less. More value of DC means that VC, more value of VC means turn on duration will be more. So make them converter turn on for the more duration, so motor can revive that condition. So motor can revive their speed or retain their speed to the set your actual speed, means whatever you have set over there, VI reference speed. Okay, means equivalent reference voltage. That's the conditions. Okay, so you are giving the TL means that load torque you are giving, so that is countering with your motor torque. So motor torque is load torque is increasing means motor torque should be increased. if your system working in closed loop in fine manner. Okay, so that's the idea. Okay, so for the converter you have to give the power circuit. That power circuit is already there, and VA means it is your output of the converter, means motor terminal voltage is coming from the converter. Now motor is connected, so isolation is required. Okay, that you know that power circuit and control circuit, there is a hell and heaven difference of that voltage level. Okay, so if you are not giving any isolation, okay, between your power circuit and the control circuit ground, so any fault occurred in your power circuit, that can damage your control circuit. Okay, that's why when you are sensing the voltage, when you are sensing the speed, so one magnetic isolation is already there. Suppose you are using tacho generator, so it's a magnetic isolation. Suppose you are using decoder, okay, speed fetching, okay, sensing of the speed. Sometimes we are also using decoder, okay, that also the magnetic isolation. So one sensor is using. So sensor means directly it's a normally you can say like it's a transducer. Okay, so you are automatically isolate that ground, okay, for your power circuit to control circuit. Another isolation is required when that gate pulse, you are giving the gate pulse to that solid state device. Okay, that portion you are giving some opto isolator. Okay, so you are using some opto isolator, means optical isolations for separating their ground. So both sides, both of the isolations you are given for your system. Okay, I hope you are able to understand. For any difficulties you are getting, so you please let me know. Again, I will re-discuss that portion. Okay, so overall idea I hope you are getting for the closed loop feedback system. So I'm just going through that points, what is written over here. Speed of the DC motor changes with the load torque. How it is changing, I think you are able to understand. So how the gate pulse are varying, okay, and the duration of the solid state device is changing, so automatically it is varying. Okay, to maintain the constant speed, okay, to maintain the constant speed, that means it is your VR, you are giving the set point value VR. The armature, okay, the armature and or field, okay, field voltage should be varied continuously by varying the delay angle. So that PWM I am telling. So here we are using ACR. So ACR, it is known as delay angle or firing angle, whatever you can say like that. Okay, of the AC-DC converter, that means control rectifier, AC-DC converter, or the duty cycle for the DC-DC converter. So DC-DC converter duty cycle also being changed. In practical drive system, it is required to operate the drive at a constant torque or constant power operation. So below base speed means up to base speed it is constant torque. Okay, and above base speed it is constant power. In addition, the control accelerations and the decelerations are required. So based on it, the acceleration, deceleration will be there. That is your mechanical portions of your DC motor. Okay, so you can control them based on your conditions. Rest of the thing will be taken care by your PWM, and based on the variation of the PWM, the motor speed and other things will be changed. Most industrial drives operate as the closed loop feedback system. Okay, the closed loop control system has the advantage to improve the accuracy. Fast dynamic response. What is fast dynamic response? I am talking about the load variations. Okay, so it will take some time. The inertia of the motor is comparatively high. Okay, so the time constant is very less in electrical circuit compared to the mechanical circuit. So your end of the day motor is increasing, the motor speed is increasing gradually, but you are considering which one? You are considering that part of your electrical circuits are there. So whatever you try to change from electrical circuit is quickly you can change, but mechanical circuit the inertia is more. So it will take some time. Time constant is more in that mechanical circuit. So instead of fast dynamics you are getting, okay, any kind of changes in the load side that TL has changing. Okay, as both are associated, electrical circuit and mechanical circuit. Okay. The reduced effect of load disturbances and system nonlinearities. So system nonlinearity means what kinds of nonlinearity? Here you can see that you are using switch. Okay, so switching nonlinearities are there. Then saturation, switching nonlinearity means switch is either turn on, either turn off, means either cutoff region, either saturation region. So these two are the nonlinear. So this type of nonlinearity is known as switching nonlinearity. Okay, of the system. So I hope you are all of you able to understand. Okay, so another important points. So block diagrams are given. Okay, so block diagrams of the closed loop converter fed separately excited DC drives given in the figure. So you can see the block diagram. If the speed of the motor decrease, that I am talking about, the speed of the motor decrease due to application of additional load torque, the speed error VE increase, that I am talking about. V is increase. V is increase means direct effect to VC. VC also increase. VC also increase means the DC value of previous condition, it is increased. Now you are comparing with the reference value, triangular. Initially that is your on time duration, this duration. Now on time duration is increased up to that value. Okay, as that control DC value is increased. So VC value is increased. Okay. So the speed of the controller responses with an increased control signal VC. Okay. Speed increase means increase the control signal VC. Change the delay angle. Okay. Change the delay angle or the duty cycle of the converter. That I have already discussed. And increase the armature voltage of the motor. Okay, so armature voltage of the motor is increased. More turned on condition is more VA. So motor can retain the speed. Okay, and increase armature voltage develop more torque to restore the motor speed to the original value. I hope you are able to understand. The drive normally pass through the transient period until the developed torque is equal to the load torque. Okay, so I hope you all of you will to understand that what I am trying to say you. Okay, so some portion is there for induction motor drive. So that induction motor drives may be discussed in my next class. Okay, next class in on Friday. So that module may be, that portions may be completed. Okay, so thank you all of you.
Thank you, sir.
Just for an important instruction. Okay, so all of you please try to ready your